Hello students, so continuing our lectures on the electronic devices, we discussed about Homo gap. So in our lecture 177, we have discussed quantum dots and the Homo and Lumo stage. Now continuing to that discussion, we must understand that under equilibrium conditions, the Fermi energy must be constant in the middle of the molecule. And we can draw this by an analogy to flow of water between water tanks. So we will assume that this metal is a very large tank consisting of water. This is the metal. And molecule, on the other hand, is a smaller tank. Let's draw the molecule, say. On the other hand is a smaller tank, just kept inside the metal. And now we will, say the water level in the molecule is like this. And so this can be considered as the Fermi level of the metal, whereas in the case of a molecule, the level is at this point, so a little lower. So this is the Fermi level of the molecule, and we make a connection between them. And so this can be also considered as the density of state. Now what happens at that? This is at non-equilibrium condition, which is at non-equilibrium, or when equilibrium has not been attained. Whereas in the case of an equilibrium case, it will happen that the Fermi level will try to balance or try to reduce the gap between them, so which will actually cause an upward flow of water here and a downward flow of water here. So ultimately what we obtain is like this. It means they attain a common Fermi level at the equilibrium. Now even after this molecule, the problem is a molecule will not necessarily have not have uniform density of states. And so and it is also possible that a fractional amount of charge is transferred. charge, it gets transferred in a molecule. And now let's for an example that suppose a fractional quantity delta n of electrons are transferred from the contact against a metal molecule contact, from the contact to the molecule. If this is the fraction of electrons which are being transferred, so it may so happen that the work function of the transferred electron, that means of these, the transferred electrons, they will include both the contact and the molecule. Since this is called a fractional transfer. Now in this case, if however if delta n was nearly equal to say one electron transfer, then it would imply that the LUMO, or the lowest unoccupied model orbital, would be half full, and so EF will naturally lie inside, lie on the LUMO, while if delta n is equal to -1, there is only one electron has been transferred. So delta n -1 means the molecule has lost one electron, whereas in the previous case the molecule has gained one electron. So in this case, when the molecule has lost one electron, it would imply that the HOMO, the highest occupied one, half full, and hence the Fermi energy will naturally lie on HOMO. Now, in general, the number of charges on a molecule on the molecule is given by n is equal to -infinity to infinity GE fraction of EEF DE, where this is nothing but the density of molecular states. Of the molecule, and so for small shifts in Fermi energy, we can linearize the effect of a charge transfer on the effect of charge transfer on EF, and we are mainly interested in the quantity TEP by Dn so this DEF by Dn, change in Fermi energy with respect of change in charge transfer. That is the change in rate, say rate of change of EF with respect to charge transfer. Now, for degenerate case, for a degenerate case, n is given as minus infinity to EF into GETE, and now taking the derivative with respect to EF. With respect to EF, we can have dn by dEF is equal to GEF. And we can rearrange this. So we have the dn by dEF is equal to GEF. So we can rearrange this and we can write delta EF is equal to delta N by GEF. So it shows that after charge transfer, the Fermi energy within the molecule it changes by delta N by G. Now, sometimes it is convenient to model the effect of filling the density of states by something called quantum capacitance. So it will give the effect of filling the density of states. quantum capacitance. CO is equal to Q square GEF. That is, so we have previously written that delta EF is equal to delta N by G. So what we will do, we will replace this G by C0 by Q square. So we get delta EF as equal to Q square by C0 delta N. So we can say that if the molecule has a large density of states, at Fermi level, the quantum capacitance is large. The quantum capacitance is large. And more, so first implication is this. Second is that more charge must be transferred to shift the Fermi level. So diagrammatically we can plot energy with respect to the density of states. Could have a plot like this. So this corresponds to this. If this corresponds to the charge transfer delta N, then this quantity will correspond to the change in the Fermi level, delta EF, which is delta N by G. So this is the charge transfer which has taken place, and this is the change in Fermi level which has taken place. So it implies that the charge transfer is causing a change in Fermi level in a conductor, and the magnitude of that change is determined by the density of states at the Fermi level, and it is expressed as the quantum capacitance.